I'm excited to tell you about what the new decadal survey, which just came out in April 19, holds for life detection this decade. I think it's going to be a very exciting decade for the search for life. But first, let me talk a little bit about the purpose of a decadal survey in case you didn't watch the briefing by the decadal co-chairs. The point is to assess the status of an entire scientific discipline, to identify key questions to be addressed in the coming decade, 2023 to 2032 in this case, prioritize the most important initiatives to address these questions, evaluate the risk and cost for recommended missions and projects, and the decadal is conducted independently by the national academies for sponsoring agencies, in this case the National Science Foundation and especially NASA's Planetary Science Division. Now these agencies and Congress take the decadal very seriously. Its recommendations are considered as the formal statement of priority, and they always state their intent to follow these priorities when making budgetary decisions and deciding which missions to fund. Now, luckily for the search for life, the new decadal has a much bigger emphasis than the previous one on the search for signs of life and life detection, etc. The terms come up something like 15 times more often throughout the report. And life detection pervades science, missions, and technology. In terms of science, there's an entire theme devoted to life and habitability, which is different from the previous decadal that was talking only about planetary habitats. Search for life was a little bit there as part of two questions, but this time it gets a dedicated question. Recommended missions to search for life are more numerous as well. The previous decadal had the Mars caching rover that became Mars 2020 that was supposed to search for ancient signs of life at the surface of Mars as well. But this time, this decadal prioritized the completion of Mars sample return, a flagship called Enceladus Orbitlander to search for extant signs of life, and for the first time, two medium-sized missions to search for life, the Enceladus Multi-Flyby mission and the Mars Life Explorer. And finally, the search for life also makes an appearance in terms of technology priorities, both in terms of instrument to search for evidence of life, as well as sample handling in situ, including pre-processing and analysis. And that is a novelty compared to the previous decadal, which didn't mention it. And those two categories for instruments are two among a few that were recommended for dedicated investments. Okay, getting a little bit into the details of the science. So the life and habitability theme has three questions. One is centered on what Earth can teach us about life. One is about habitability, and this third question, which is question 11 of 12, priority questions, is the search for life elsewhere. Is there evidence of past or present life in the solar system beyond Earth, and how do we detect it? So I'll take this one as an example. Each question in the decadal is subdivided into subtopics, in this case the path to biogenesis, biosignature potential, life detection, and life characterization. And for each of these sub-questions, the report sets out a list of strategic research points to be addressed in the coming decade. In this case, the strategic research avenues center around the development of payloads, including early integration of sampling and analysis suites, a search for evidence of present or past life or life as we don't know it, using strategies informed by RNA on Earth, lab, theoretical, and field work, and then the development of techniques to mitigate contamination and avoid false positives when trying to search for signs of life. And this is done through modeling as well as improvement of hardware protection and/or cleaning. Now, in terms of missions, the top priority is to complete Mars sample return for the entire robotic exploration program for planetary science by NASA. MSR has 7 objectives, and the search for life is objective 2 of these 7. So I won't go into the details here. You can read this IMOS report from a few years ago. But the search for life requires looking for signs, patterns in the carbon chemistry, and signs of ancient and modern biosignatures with a number of subdivided objectives and investigations there. In addition to the completion of Mars sample return, this decade will prioritize 2 flagship missions. The top one is a Uranus system mission, and the second, if budget allows, is Enceladus Orbilander that includes 5 objectives related to the search for different signs of life listed in light green on the left, 1 through 5, plus a number of objectives establishing context for the provenance of samples and the habitability of Enceladus. This mission would carry a payload of something like 12 to 13 instruments, both to search for signs of life and to establish this context. And its timeline would require a late start in the decade. This is because all the excitement happens at the South Pole of Enceladus, where the jets come out, and the South Pole will be in the polar night in the 2040s, so the mission has to get there afterwards in order to perform reconnaissance of the surface for landing and then communicate with Earth once on the surface. Earth has to be in view. So that's why it was not a fast priority early in the decade, and it might have to be initiated next decade. We'll see. If that's the case, if there's no budget for it this decade, the decadal committee, who was so excited about the search for life at Enceladus, provided another avenue to do it within an Enceladus multiple flyby mission, in which case the mission would be cheaper. It would have to go through a competition with other concepts. The number of objectives would be a bit narrower as a result, and the payload complement would be smaller as well. But this mission could search for life in the plume with a bit less certainty than the Enceladus Orbilander, and still be a very excited mission. If the budget constraints allow, another mission past the Mars sample return could be initiated, the Mars Life Explorer, and the idea behind this mission is to drill into the surface to search for signs of extant life on Mars, including organic molecules, non-equilibrium gases, isotopes, and then complete a suite of objectives to again establish habitability and the sample context. So for these missions to happen, technology development was specifically emphasized toward the end of the report, just as it was in the science sections, reiterating the need for integrated instrument suites, mitigation of contamination sources, improved front-end sample handling, as well as specifically for sample handling, a warning that these will need to be available this decade for the priority missions to take place. And this includes sample collection, separation, and detection of what it contains eventually. So that's it. I think it's going to be a very exciting decade, and I will leave you with this summary slide, and thanks for listening.
Hello, everyone. My name is Kate Kraft, and I'm a planetary scientist at the Johns Hopkins Applied Physics Lab. I'm excited to talk to you today about the future of the Search for Life workshop. So in this workshop, we really wanted to think beyond the state of the art. What signs of life should we be looking for when we start to think about 20 years plus in the future? What are those signs of life, and what levels of detection are needed to make observations and discoveries of these? So we put together a good mix of engineers, scientists, those interested in the planetary realm, those from industry and early careers. And we got those folks all together so that we could get a good mix of folks with different interests, backgrounds, and ways to inspire each other and learn from one another. Those who are interested in the outcome of our workshop includes Mary Wojtek of the NASA Astrobiology Office, Carolyn Mercer of the NASA PESTO Office, which is the Planetary Exploration Science and Technology Office, and those of you, many of you attending today who are in the Network for the Life Detection, which is an interdisciplinary consortia for astrobiology research, or ICAR. The workshop took place over about 2 weeks in March and April. They were half days. It was fully virtual and consisted of small breakouts where we would get into the smaller groups that really allowed us to converse better and get our ideas mingled with one another. The workshop really focused on brainstorming and educating in the beginning. We wanted to ask our question, what are the signs of life that we should look for? And at what ranges and resolutions? So really getting down to those measurement level requirements and putting numbers on our measurement requirements. We didn't want to go with just the normal signs of life, like more traditional ones that we have instruments for today. We wanted to think about looking out there into the future. We also wanted to engage those from outside the usual NASA backgrounds. And we also wanted to really engage the engineers in learning more about the development of our science measurements and learning from one another, exchanging ideas between engineers and scientists. And then, of course, when we think about bringing those in from outside of NASA, they might not have as good of an understanding of mission concepts, of mission requirements and constraints. And so we did some educating early on where we looked at previous mission concepts, including Europa Lander and the Enceladus Orbilander mission concept studies. We also heard talks about the Life Detection Forum, the Life Detection Knowledge Base and Taxonomy, and we also discussed at length what a science trace matrix is and how you work from your science question down to the measurement requirements. We worked hard to inspire everyone at the workshop. So we heard talks on life at destinations and Earth analogs, including those at Mars, subsurface oceans, life in ice. We heard about the Dragonfly mission and its target of interest, Titan, the moon Titan at Saturn. And we also heard an interesting talk about agnostic biosignatures. We also had fun watching some films or little clips that teams have made about exploration platforms. So what are the platforms or these bots that would be taking our instruments to these worlds to make our life detections? So we heard from a group about a Titan submarine exploring the depths of Kraken Mare, an Enceladus Vent Explorer that you can see at the bottom right, an artistic impression. We heard from a team called SWIM, which is sensing with independent microswimmers. Bots, tetherless deep drilling into the Mars South Polar Layer deposits, which a picture is shown up there at the upper right. And also a project called Breeze, which is a bio-inspired ray for extreme environments and zonal exploration, such as could be performed at Venus. So as the week progressed, we also then had the teams, or had groups kind of start to break out into different targets of interest. So we polled everyone and saw where folks' interests lie, and we came up with the group of target bodies listed here, and target environments as well within those bodies. So we had a group called the Ocean World Plume Group, Europa Ice, Europa Subsurface Ocean, Mars Subsurface, Mars Ice, Enceladus Subsurface Ocean, Enceladus Icicles, and Titan Seafarers. And then after the first week of really pinpointing what exactly biosignatures of interest we had and thinking about the measurements that would be needed and the resolutions and really getting to the numbers, we really came to understand that several of these biosignatures of interest were some of these newer ones that we were more interested in. And so we picked those out from all the brainstormed ideas that came from the first week, and really took these 4 biosignatures of interest and really made sure we had all the details there that were needed. So we looked at biofabrics, which as you can see a small picture of in the upper right, but those in particular would be biofabrics and ice. We talked about catalysis. We looked at dynamic disequilibrium signatures, and we also looked at informational polymers, such as you can see a picture of at the right here. And so what we started to think about with these biosignatures was, do we really have all the information here that would allow engineers to have those numbers and those details that they could take that information and move it into a technique or an instrument. And so this was a place really where we wanted to hear from the engineers. Do they have everything, all the information they would need? Do they have the observables named and detailed? Do they have the measurement range? Numbers, give me the numbers. And then also any context measurements that would be needed to be made alongside of the main measurement. And then once we had all of that figured out, we had another film festival to continue with the inspiration and motivation, keep everyone excited. And we started to think about the other aspects of making these detections. The sample acquisition. We started with thinking about the sampling site of interest. What did we care about scientifically? And then what sample characteristics that will we need to be preserved as we bring in our sample of interest or just do the analysis? And what challenges are associated with the acquisition in that particular environment? So an example at the right, we had a team that was looking at the ocean of a subsurface icy ocean world. And they thought about these different regions within this environment of where they would want to sample. Within the pelagic ocean, at the water ice interface, and also at the water rock interface near a vent. Then once we have the sample, once it's been acquired, we needed to think about the handling and preparation. What state does a sample need to be in for the analysis? What characteristics needed to be preserved? And then how did we envision processing the sample to access our indicator of interest? The teams also had a lot of fun coming up with team names and artistic representations, such as the SPORE team at NfoLD. So really, in summary, heading into the future for the search for life, the workshop, the fossil workshop findings will be published. And the intention of this effort is to summarize, identifying the biosignatures, some of these kind of newer or maybe not as traditionally focused on biosignatures of interest, coming up with the measurement requirements. And then this information allows for scoping the technology and mission developments that are needed. We also really focused on strengthening and deepening understanding and knowledge exchange between engineers and scientists, but we really only scratched the surface with this. Really to enable life detection into the future, more of these types of interactions and engagement would be greatly beneficial. Thanks for your time. Look forward to seeing you at the meeting.